In this lesson, we will discuss fractions and some fraction misconceptions. Often, when I mention the word fractions, the first response is a groan or a complaint along the lines of, "I hate fractions." I believe this is because, over time, fractions have been a bit harder for students to understand. I really love how the Focus in Math Now provides more use of visuals for students to understand the mathematical concepts such as fractions. Students are then given the visual understanding of fractions before moving on to the abstract. In this lesson, we will talk about different aspects about fractions that your child will learn this year and in coming years. In third grade, your child will be working with fractions with the denominator of 2, 3, 4, 6, and 8. The denominator is the number on the bottom of the fraction bar, representing the number of equal parts. Sometimes fractions use a diagonal bar as well. Students will be exposed to both representations, but most commonly in algebra, the number on top and bottom of a bar is how fractions will be represented. Fractions require students to not think of the numbers as separate, but rather combined. They make a single value made of two parts. If someone looks at a fraction 3/4, they can immediately see the numbers 3 and 4. If I were to label these on a number line, it would look like this. But when 3 and 4 are used in the fraction 3/4, this number is now somewhere between 0 and 1. It represents part of the whole. The whole is broken into 4 equal parts, and 3 of the 4 equal parts are being considered. When placing whole numbers on a number line, we can put them in sequential order. For instance, 1, 2, 3, 4, 5, 6, and so on. When placing fractions on a number line, such as 1/1, or 1 whole, 1/2, 1/3, 1/4, and so on, they are not in sequential order according to the denominator. In fact, the numbers go just opposite when the numerator is 1. 1/6, 1/5, 1/4, 1/3, 1/2, and 1/1, which is 1 whole. Now let's discuss the difference between additive reasoning and multiplicative reasoning. First, we will show additive reasoning. I can state 5 is to 6 as 10 is to 11 because I'm adding 1 to the first number to get the second number. Multiplicative reasoning can be shown as 5 is to 6 as 10 is to 12. We are multiplying 5 and 6 by the same factor of 2. When comparing whole numbers, I use additive reasoning, such as if I were to compare 6 and 4 or 10 and 7, I would find the difference between the two numbers. I cannot use this thinking when it comes to fractions if the numerators and denominators are different. If I am comparing a fraction, I need to look at what the fraction represents. In fourth grade, your student could be presented with a problem to compare 4/6 and 6/8. If the student were to draw a rectangle on graph paper made up of 6 equal squares and shade 4 to represent 4/6, then if the student were to draw a different rectangle composed of 8 equal squares and shade 6 to represent 6/8, the student would not be able to compare these fractions using this model. The reason is because when we compare fractions, the whole needs to be consistent. In the representation just presented, one fraction has the whole made up of 6 square units and the other is made up of 8 square units. Let me model this correctly. This time I will represent my fraction with the same rectangle representing the whole, made up of 6 rows of 8. Multiplicative reasoning will make it easier when I shade the amounts of 4/6 and 6/8. First, I will shade 4/6. I would then color in 4 of the 6 rows. My next rectangle will be the exact same size, representing my whole. I will shade in 6 of the 8 columns. I could count how many square units are shaded in each to determine which fraction is greater. 32 square units are shaded in 4/6 representation, and 36 square units are shaded in the 6/8 representation. My model then justifies that 6/8 is greater than 4/6. When using operations such as addition, subtraction, multiplication, and division, we need to look at the numerator and the denominator as a single entity. For example, 1/2 plus 4/2 equals 5/2. In whole number multiplication, the product is always bigger. 4 times 6 equals 24. 3 times 8 equals 24. When whole numbers are multiplied, the product is larger than the factors. Although, in later grades, when your student is multiplying fractions, the product is smaller than both factors. I will show you this using graph paper. I can draw 1/2 times 2/3. First, I will shade in half of this rectangle. Then I will shade in 2/3 of the rectangle. The amount overlapping represents 1/2 of 2/3, which is 2/6. So 1/2 times 2/3 equals 2/6. You can see 2/6 is less than 1/2 and 2/3. Last, it is important to recognize that fractions can be represented in decimals and percents as well. 1/2 can be represented as 5/10 as well as 50%. In this lesson, we covered an overview of fractions. Keep in mind your child won't be learning all these concepts this school year. Students are presented concepts year after year, and each year builds upon the previous knowledge. This lesson was designed to give you a little preview of concepts and how they progress and build upon each other. Today we were able to discuss a variety of fractional concepts as well as some fraction misconceptions. In this lesson, we covered fractions being viewed as a single entity, additive and multiplicative reasoning, operations with fractions, and different ways to represent fractions.